Good evening. So in a previous video I had wanted to talk about Zimmerit. I don't know if you know what Zimmerit is, but you've probably seen it. If you have a vague interest in tanks, you might even have heard of it. It's that weird and unusual, often misunderstood textured material applied to some German tanks. The reason to talk about it is because I wrote a book on the British work on that type of material and similar subjects. This book, in fact, British Zimmerit, Anti-Magnetic Mine and Camouflage Coatings, 1944 to 1947. Yes, I'm aware that goes past the end of World War II, but believe it or not, military technology did not end with the death of Hitler or the surrender of Japan. So, this book came out in, whatever it was, 2020. Yep. 2020 this came out, and this was commonly quite a bit of work looking at various elements of British views of this German material and how the British sought to use the material for their benefit. So let's cover a few basics first so we know what we're talking about. So we should all hopefully know that Zimmerit is an anti-magnetic mine coating. What do we mean by this? In a nutshell, the material creates a gap between the steel surface of the tank and an explosive device using magnets to adhere to the side of the vehicle. Now, both in my 2016 article for Tanks Encyclopedia, linked below, and in my book, I put that work on the German substance began in 1943. DB and Alkit factories started using it on tanks from around November 1943, and an official order from German High Command, the Oberkommando der Heer, followed in December. As we go on, we've got a little bit more learning to do on the subject. So, however, the idea of applying a material to the surface of tanks began a little earlier than this. Now, partially lost and obscured a little by the mists of time is the development process on the German side. But thanks to a pointer from Herbert Ackermanns, a document was located in the German archives showing that work on something, a material of some kind to stop magnetic mines from sticking. Well, obviously they don't stick, it's a magnet, but let's try and avoid use of the term sticking. It doesn't even adhere, it attaches itself magnetically. But work on some material of some kind to stop magnetic mines being able to magnetically attach to the side of a tank was already underway by at least June 1943 by Zimmer. Now, the document in question refers to army tests carried out by the Versuch der Heerwachenamt. That's the Army Weapons Office back in January 1943 on possible methods to use defensively against magnetically attached mines. This suggests to me that the idea must have been around at least a little earlier and pushes the Zimmerit concept a little further back, perhaps into the end of 1942, possibly again tying in with the arrival of the Haftholledung magnetic mine in German service late in that year. So it's quite possible that as the Haftholledung enters service, well, at the same time the Germans are thinking this is a great device, how do we come up with a method to protect our own vehicles against it? Nonetheless, the idea all along was clearly as a protection against explosive charges, rather than anything else related to camouflage or a physical armoring put on the surface, or even a protection against fire. I don't mean actual like fire, I mean literally physical fire. So options thought of by the Germans clearly at this early stage, tested, considered with the use of a thin cement, a Betonmilch, presumably applied roughly by hand. Anyone who's had the fun of mixing cement in a wheelbarrow with a spade will attest to the fact that if you don't clean your spade off afterwards, the cement really does like to stick to steel. So use of a thin cement in this terms creates that small gap. And if you know anything about magnets, you'll know that as the distance increases, the magnetic power by which it can attach decreases exponentially. So a small gap has a large effect. The second option is a spray-on form of a thin cement mixed with a fine-grained chipping of some description, doesn't say what it is, to produce a layer between 3 and 5 millimeters thick, and this is plenty thick enough to affect the magnetic adherence of a charge. Option number 3 from the Germans was a coating of bitumen or tar into, once again, which fine-grained chippings could be applied. A note of caution here, though, was that this material was not suitable for use in hot areas. Now, a note of additional caution from me is that is not saying that the materials are flammable. Yes, bitumen and tar are technically flammable. It is, however, not easy to set them on fire, and the hot areas in this context is more to do with ambient environmental heat causing the material to soften or even flow, so slumping of that down. This is definitely something that I found as a problem in my research into British plastic armour, which is a forthcoming book, hopefully by the end of this year. So that's a far better take on it than bitumen will go away from because of flammability. Makeshift methods is the fourth option, and that's basically applying oily substances, again things including bitumen, tar, but also thickened oils to the surface of a tank to stop the mine from adhering magnetically. Apologies for the little glitch there, little power cut. So anyway, oily substances, tars, whatever else that could be smeared in a rather ad hoc or makeshift manner across the surface to stop magnetic mines from magnetically fastening to the steel of the tank. These were also identified as not being suitable for hot areas for the same sort of reasons, and these are also likely to create additional problems because if we're allowing this ad hoc methodology to take place, we're also going to start using substances which are going to be more into that flammability, ease of flammability range. So that's going to be a problem. We don't want our tanks catching fire. So that was number 4. And the final option, and perhaps the oddest idea you might ever have considered, is the one of covering them in water. Okay, what's that mean? We're going to cover our tanks in water. Yes, because remember, we're talking about Russia primarily in winter, and boy, does it get cold in winter there. I mean, it gets bloody hot in summer, so this idea was completely useless for anything other than winter. But yes, they're going to cover the tanks in water to build up a layer of ice on the surface to prevent the mine from adhering. For very obvious reasons, that option is totally impractical. For example, not all of the crews would be happy driving around in a giant ice cube. This plan is also going to adversely affect all of the functioning of the vehicle, not least of which being the crew, who are probably going to freeze to death. And also parts of the tank are going to get warm, namely around the engine bay anyway, where that ice will probably just flake off. Plus the adherence of large sheets of ice to smooth metal isn't going to be good when it starts getting hit with bullets. So it was an idea. It would have been interesting. I would love to have seen them do some testing with it, but perhaps thankfully for everyone that didn't happen. But that was one of the ideas. And again, all they're doing is really brainstorming around the idea of how do we build a gap 3 to 5, maybe a bit more, millimeters thick on our vehicle, particularly on the flat, smooth surfaces where the Haftholder could adhere easily with its magnetic feet. So there are photos around of German vehicles with cement on them. It does look like cement rather than Zimmerit. And that's specifically a Somua S35 and a 38H as well. And these were captured by the Russians, I believe in 1945. And these would have been an ideal vehicle on which to test a coating like that in 1943. By 1943, those vehicles were completely obsolete anyway. So it is possible that those vehicles were captured by the Russians, being left with this material on. rather than maybe it was applied later. Now, that's a bit of speculation on my part. I haven't looked a great deal into the history of some of the testing taking place at places like Kummersdorf, but that is an interesting potential answer as to what on earth was going on with those vehicles. Nonetheless, what we can deduce from this is that by the time of that letter, there were clearly no good ideas that were suitable. I mean, bitumen and tar, ironically, as we move on, you'll see the bitumen option was used by the British and they did like it, but it's also going to be running into some of the production problems for the Germans. They have some material shortages. Maybe that was perhaps a little more than what they were thinking. Cement, likewise, is a valuable commodity at the time that was successful. It's obviously not flammable, but it is a valuable material. Bitumen being rejected for its fire risk, honestly, I do have to think that's a little overstated. If anyone has ever seen a roof being retarred or resealed, you will know it is far from simple to set fire to stuff like that. It does tend to soften and then melt first. So I do think that concern is a little bit overstated, but it's not a zero concern. So having got to that point, right, they've looked at some of the options, everything from bitumen, ad hoc methods to ice. They clearly needed a bespoke material. And that's why this new Zimmerit has come around. Now, when I say Zimmerit, I'm not just talking about that exact material, but rather in the way that some names, particularly brand names, might then go on to be the name for a collective group of products. Someone in America might say, pass me a Kleenex when they want a tissue because Kleenex is synonymous with the brand. Or I'm going to, quote, hoover this area instead of I'm going to vacuum clean it. So I might use a Dyson or other brand to hoover something up. In the same way, a Zimmerit kind of material, because this is the most famous, to me what it is this generic brand. But this new material, this genuine original Zimmerit, was created. So sometime between the testing in January, they've decided that they needed something else, and the General der Schnellentruppen, the General of Fast Troops, decreed in a letter on 9th of February 1943 for just such a material, and this was ready by the start of June. The first tests that we know of Zimmerit took place between the 5th and 8th of June 1943 at Kummersdorf, and they must have been successful because on the 30th of June we know that it was being ordered for vehicles belonging to the 4th and 7th Panzer Divisions. Just for reference, 7th Panzer Division was being moved to the Eastern Front from France in February that year, and 4th Panzer Division, which had been on the Eastern Front since Operation Barbarossa in June 1941, by the end of 1942 was a shadow of its former self, depleted by combat. So both units were then going to be used in the Battle of Kursk in July and August 43. So this new scheme may well have been intended for use during that campaign. Again, that is a little bit of speculation on my part, but it does tie in nicely with the idea of we know we're going to have a big campaign. We're going to do a big push against the enemy. It's going to be a brutal fight. We want to make sure we're as well prepared as possible. And just before we draw a line under this little German segment, I've got to remind you once more, the substance was specifically identified as, excuse my German, Gegenmittel gegen Haftsprengladungen. That is an antidote to explosive charges. So expecting or maybe concerned over the use of, the Russian use of magnetic charges, this Zimmerit has come around. Now, for the Germans, the material itself was applied in 2 layers up to around 5 millimeters thick. Layer 1 applied with a trowel on top of a primer on the bare steel and takes about 24 hours to dry. A second layer was then applied by metal comb and dried either by blowtorch or left to dry in the air. In either case, it in the latter case, it would take about 8 days to harden. So first use of Zimmerit comes around in the summer of 1943 as it's being ordered and started to being applied on German camps, as I say, I think for the autumn campaign. And this ties in nicely with when the Russians got hold of examples of the first vehicles they had with this weird, unusual coating and did some experiments of their own. Here, the Russians were quite legitimately confused by what on earth this stuff was. So the first maybe was a thought on perhaps it's something to do with extinguishing fires, though quite how the mechanism of that would work is unclear. And the second idea was some kind of clever camouflage. However, as I said, German records have seen so far say no such thing, but the speculation by the Russians is perfectly valid considering there doesn't seem to be any notable use of magnetically attached charges by the Russians at this time. Their examination of it for reference showed the material to be 53% barite, barite is another name for barium sulfate, 16 to 17% quartz, 27% organic material, and a further 3% of something unidentified, possibly partially due to contamination. So having looked at the formula from the Soviet Russian point of view, we can compare it with what we know of the German recipe, and the two things differ quite significantly, and the reason for that is completely unclear, and it does suggest either a different substance or some failings within the testing. But the German recipe should be 40% barium sulfate, 25% polyvinyl acetate, 15% goethite or limonite or a mixture of the two as ochre pigment, 10% zinc sulfide, and 10% sawdust. If we allow the benefit of organic material being mixed in with something like the zinc sulfide, the ochre, then that might account for that 27% organic material the Russians identified. I don't know. There's no real good answer, but I think it's very notable at the time that the Russians were interested in it enough to do some testing and wonder what on earth this stuff was. The more important part is that despite the Russians finding this odd stuff in autumn 1943, they didn't seem to think a great deal of it. It certainly wasn't stopping them destroying German tanks in good numbers. But they also didn't bother to tell their allies, the British, because the British first came across this stuff in summer 1944 after British analysis of the material when they first found it brought it out to be material about 4.5 to 6.4 millimeters thick, substantially thinner therefore than originally intended, and the British also did chemical analysis on the material, and that's how they found it. 40% barium sulfate, 25% polyvinyl acetate, 15% various forms of iron oxide, that's your ochre pigment. They put that down as red ochre for reference, 10% zinc sulfide, and 10% wood fiber. Notable here for people who are concerned or might be talking about the flammability note is that barium sulfate has a melting point of 1345 degrees Celsius. Polyvinyl acetate unbonded has a flammability point of 104.4 Celsius. Red ochre is completely non-flammable. Zinc sulfide is non-flammable. The wood fiber added, yes, they're flammable, but once bonded, they just char. So real as a flammable substance? No, it's not a flammable substance. So let's put that little rumor / myth to bed. By the time the British are here in northern France, busy trying to kick the Germans out, they're also now finding their own problems with magnetic charges, amongst other things. So the Haft-Holder was knocking out some British tanks. And report FT 1421 of 1944 says short and simply, it says it was required to find a solution to the magnetic grenade problem. And though the options available to the British in 1944 are interesting because in some way they mirrored those early 1943 ideas from the Germans, although not ice, thankfully. For all of the silly ideas that might have happened, that was not one of them. British ideas did come up with a few possibilities. Wire netting, a paint/gravel mixture, cladding tanks in plywood, covering them in bitumen plastic, spraying them with a coating of asbestos, or some sort of Zimmerit. Now, the wire netting couldn't exert enough force to get through the distance that wire netting could create, but equally, if you got that much soft wire like chicken wire netting, the concern was that the Germans would simply wedge the mine into it anyway, not to mention the fact it would be easily damaged by passage through the undergrowth. A paint and gravel mixture was a very good idea. Indeed, we have textured paint in use since at least World War I, things like helmets, adding crumbled cork into the paint mix to create a textured surface. The main problem with a paint mixture is the difficulty in drying it. Cladding your tanks in plywood is kind of an odd idea. That would have been a really interesting concept for a modeler's diorama, but fitting wooden panels over a tank is not easy, especially considering all of the curved surfaces and angles. Repairing it in the field would be difficult, and the Germans could quite simply have got around it with a magnetic charge fitted just a metal ring with some spikes on it. And indeed, one of the magnetic charges, the Germans had a smaller magnetic charge for that reference, did have exactly that. So the magnets would attach to a steel ring, and the steel ring would have little spikes on it, and you just come and stab it onto a wooden surface. So cladding your tanks with plywood would have worked in the short term. It would have been expensive, it would have been difficult, and it would have been very easy to counteract. So that was disregarded. And what that left with was the option of bitumen plastic. So this material had the advantage that it could be mixed with fabrics, woven asbestos, hessian, or even a type of fireproof felt. Layering that onto the vehicle, stick it onto the material, put the fabric on, spray it with bitumen, you get a nice thick coating. And as long as you could make it stick to the vehicle, you could create that gap that you need. And the adhesion to the vehicle here would be the main flaw. Another good option was sprayed asbestos. Whilst today we run a country mile away from everything with asbestos because it's a terrible substance for human health, it is an excellent material in terms of insulation. It creates a very good coating. It's quite obviously not flammable. It's very tough and abrasion resistance, and it could be relied upon, stuck onto a vehicle to create the gap that was needed. And the last option was simply to copy the German material. After all, we knew what it was made of. It was known to be effective, but here we have a problem of wartime. The ingredients in the German material were simply too difficult to get hold of, namely that polyvinyl acetate. It was a very difficult substance in very short supply at the time. So, wire netting, paint gravel, plywood, bitumen, asbestos, and Zimmerit. 6 options, and the best 2 quite clearly out of that are bitumen and sprayed asbestos. So, perhaps improving the bitumen with a fabric of some kind, spray on or attaching asbestos sheeting. We needed some kind of material in the account which would have desired features. And the desired features were laid out very quickly during the war. After this material was found, it would have to have a corrugated surface, it would have to have a good strength, it would have good keying to painted surfaces, as in we could apply this onto the surface of a painted tank and it would stick to it pretty well, and it would set quickly to a thickness of up to 4.8 millimeters. That all sounds very good, but there's a lot of work that goes into that. And later on, this whole corrugation of the surface would actually be disregarded because there's no real benefit to that other than perhaps reducing the amount of material involved. Nonetheless, those key features were identified, and British work on Zimmerit began on 28th of June 1944, at which point 4 additional requirements were also added in. Namely, the material, whatever it was that was chosen, would have to be weatherproof and suitable for use in a temperature range up to 88 degrees Celsius, which is 190 degrees Fahrenheit for people who prefer Fahrenheit for some reason. That's ridiculously hot. That's obviously hotter than any part of the world in which we're going to be using tanks. So this is simply making sure that no matter how hot it gets, the material isn't going to slump, crack, or melt off. The material would also have to resist immersion, so it better not be water soluble because we're going to want to use tanks during wading operations. The material should obviously not be flammable. We don't want to cover tanks in flammable materials. And this would be tested using a flamethrower with thickened fuel. And the easier it was to apply, the better it was going to be. So with those details identified, in July 1944, Sherman T-74199 was fitted with a variety of substances. So Sherman T-74199 is interesting not only because of these trials, but also because it's one of the very first Sherman tanks the British received. Now, the tank was covered all over different faces with different mixtures of the Zimmerit. And this was given a letter code, and the codes were A, F, P, and H. Letter A was for the woven asbestos fabric. Letter F was the felt quilted on Hessian. Letter P was bituminous plastic. And letter H was a 4-ply Hessian fabric packed with bituminous plastic. Having been covered with these materials, the tank was then sent on a rather excessively difficult off-road driving course around Chobham Common, driving through trees and heavily overgrown areas. And after the first mile, the first problems began to show. On the left-hand side, the near-side front drive housing, the inner face of that, which was covered with felt, had split completely down the centre. It was now only partially sticking to the Hessian, to which it was quilted, and it was also only partially sticking to the housing. Now, this is not maybe surprising, because this is the very front edge of the tank, hitting the scrub as it travels through the woodland. Over the next set of mileage, so they've now done another 19 miles, so by the time they've reached the 20-mile point through the woodland, more tearing, including to the offside rear asbestos panel, has also taken place. And that was ascribed not to a weakness of the material, but a weakness of the adhesive, which was in use. In fact, that whole piece of fabric was torn off in its entirety. After just another mile, so by mile 21, the adhesive near the engine exhaust outlets had become too hot. Whatever adhesive they were using was not suitable, and it had started to become too hot and was smouldering. By mile 25, the felt quilted on Hessian material and the 4-ply Hessian on the near side of the tank had also torn off. 4 more miles were then carried out, so in total they'd done 29 miles. No additional problems took place in those last 4 miles. Then they continued on until the 47-mile point, and no additional defects were found. The end results, however, were a very scruffy-looking tank with the majority of damage around those projecting final drive housings. And obviously the material isn't going to protect the tank if it's torn off in patches. After the test with the Sherman came a Churchill trial. T32182 was coated with bituminous plastic, 3.2 millimeters and unreinforced across the glasses, hull front plate, side pannier, air louvers, the lower rear hull plate, turret front, turret rear, turret sides, turret roof, the turret stowage bin sides, rear and roof as well. The sand shields had no preparation on them at all. The hull rear got what was called preparation B, and it's still bituminous plastic, but here what they did was they put on the 3.2mm thick plastic, stuck on a layer of Hessian as a reinforcing fabric, and then put on another 3.2mm layer of Hessian for a total thickness of 6.4mm. So technically we have two types of bituminous plastic on trial here. With the plastic stuck to the tank, Churchill 32182 was then sent on a mileage trial. 114 miles were done cross-country, no defects were reported. Another 12 miles were then done on the road, still no defect. And then at the 126 mile point, the vehicle was then sent into the woodland. And we know from the test on the Sherman tank just how aggressive and damaging this woodland trial was. To the extent that by mile 128, so just 2 miles into the woodland, excessive damage had been caused to the sand shields on both sides due to tree branches being picked up and then being dragged around. Now, remember, neither sand shield had the plastic composition on, so this is just an indication of just how aggressive this course was. By mile 138, so after just 12 miles of woodland driving, the sand shields were in such a bad condition that apart from one little section at the front, they had to be cut away just above the fixing bolts. The side panniers were scratched on the bituminous plastic. The front-facing section of each air louvre had also been partially worn off, exposing the steel hull underneath, and the hull upper rear plate, that composition B, was already starting to get torn off on a lower corner, so it should be clear by now that composition B was unsuitable. The trials then continued up to 146 miles in total, and so between mile 138 and mile 146, the material on the sides of the turret and stowage box was recorded as having been heavily damaged by tree branches carried around the tank and by the tracks, because remember, by this time the sand shields are now being removed. Part of the material on the stowage bin had been completely ripped off. The near side, that's the left-hand side, pannier plate was missing a small strip of material. The front sections of both air louvers are now completely exposed, and the coating at the front where the nose met the glasses was worn away as well. In fact, as a little addition here, the report even noted that the driver's boots had damaged the coating on the glasses when he's been entering the vehicle. So this bituminous plastic is a relatively thin, 3.2mm thick, and soft material, and this driver's boots presumably had metal studs, segs, in them, which have caused some damage there. So, in total, we had the two compositions, composition A and composition B, and although there had been damage, remember this was an incredibly aggressive course, and the conclusion overall that it was robust as a material. So it did pass, although it's not perfect, and obviously it's also black, so it still needs repainted. The tank was then sent, in this condition, for wading trials at Westward Ho in August to see if the material affected the waterproofing efforts. Now these waterproofing efforts, as we touched on in a previous video, were to make sure the tank didn't fill with water when being landed from a landing craft. In this case, the Churchill was prepped for its 6 meter wade, that's 1.89 meter deep wade, and the effect was the side doors were found to leak, unfortunately, and they had not had any additional work done on them other than this, so the side doors were a continuous issue. The cord text, that's that rope-like explosive material used to blow off the waterproofing fabric around the mantlet. When that was detonated, it was also found that this explosive damaged the coating as well. After this, firing trials were then carried out. They used .303 armor-piercing ammunition and 15mm Baser armor-piercing ammunition against the tank, and very little damage was caused by these bullets against the bituminous plastic. Using 6-pounder armor-piercing shot, one single shot removed half a square foot, so 0.05 square meters of plastic, and loosened some more around it. 25-pounder high explosive was extremely effective, and a single shell stripped off an area 4.5 foot by 2 foot, so that's 0.84 square meters worth of material off it. And attacked with the flamethrower, remember the early concerns we talked about with the Germans worried about flammability issue? Well, here we have a tank covered in bitumen, tack it with a flamethrower, the material performed well. The only failure were on the very thin metal surfaces. What burning took place didn't actually catch fire. It was in the form of light charring on the surface and some localized blistering. But the material did not soften and no material was lost. So, bitumen was superior to the first asbestos trials because that tank had ended up being ripped apart by the Woodland course. But new asbestos trials would then have to go forward in August and September 1944. So with those tests out of the way, the next was asbestos again, this time with expanded metal. So Sherman T232666 was fitted with asbestos 3.2 to 6.4 millimeters thick across the glasses and hull sides and across all faces of the turret, but not the roof. The skirting plate on the near side, likewise, but on the off side, the right side, it was improved, so it was thought, with a layer of expanded steel to improve the resilience. This vehicle was then taken on extensive trials in the same Woodland for 158 miles. After 103 miles, severe damage was found to the material on the front after a collision with the tree stump. Thereupon, for the rest of the mileage, so the remaining 55 miles, at the end, severe damage to the material at the front was found, and the remaining material were only stayed fastened, apart from a couple of small patches which came loose. So overall, the material was resilient and resistant, certainly better than the previous one was, but still not ideal and liable to damage.
So after asbestos and bitumen, not much had been done to create a material robust enough. But despite this, there was clearly promise, and the materials had worked regarding mines. Black bitumen-coloured tanks or white asbestos-coated tanks would need painting. And if a new substance was going to be made to imitate German Zimmerit, it quite obviously made sense to have it do all the camouflaging work at the same time, i.e., we ideally want a material which is green. So, as an alternative material, had already started with contracts going out to paint makers whilst those Sherman and Churchill trials were going on. That was built into it. And the requirement sent out to the paint makers was that the material must provide a rough corrugated film up to 12.7 millimeters thick. It must be applicable in the field by trowel or in just 1 or 2 coats. It must dry within 8 to 16 hours at ordinary temperature, and they wanted to make sure that time could be reduced by using a blow lamp. It has to stick to the steel, whether the steel is painted or not. It's got to resist immersion in water. It's got to resist high temperatures. It's got to resist the humidity of a tropical climate. And here we're already thinking about work on this material being considered for use in tanks in the Far East against the Japanese, a country which, by the way, had excellent use of magnetically adhering mines, which were very dangerous. The material also had to withstand vibration from the engines and guns. It's no use putting this on the tank and driving it away and having it flake off. The colour, however, was declared not to be important, but if possible, olive drab was desired. So they're wanting it coloured, really. If you got these as a potential contract as a paint maker, you would make whatever efforts you could to make sure that you got the contract by making it fulfill their desires. It is from this point on that the material is often referred to on and off as plastic paint, even though the term plastic paint is technically only applicable to one of the 2 alternatives being considered at the time. So just get your head around how much fun that is to try and discern from letters about plastic paint quite which plastic paint they're talking about at the time. And the reason I say 2 is because there are 2 different paints being considered. The first one is a shellac-based paint made by Messrs. Mander Brothers Limited, and the second one is the plastic paint which is an oil varnish material supplied by Messrs. Smith and Walton Limited. So we have to compare the two of them. Both of them could be sprayed on. The oil one could be brushed on, the shellac one no one was sure about. The oil one could not be applied by trowel, it appears, but the shellac one could. Both took quite a while to dry, the oil varnish a little quicker, troweling being the longest time for everything to dry. And in terms of drying time, application time and man hours, though, the shellac one was better, quite substantially better. In fact, 20 to 28 man hours to apply the shellac, compared to the oil varnish, which, because it required a third coat, would take over 5 days to dry. So, quite clearly of the two, the shellac one was superior in those terms. Now, both of these materials were subject to firing trials. Obviously, people like to shoot at tanks during the war, so we need to make sure that the material is robust. And firing trials were conducted in January 1945. Here, armor-piercing shells, high-explosive shells, and other chemical attack were tried, as well as flamethrower. Flamethrower-wise, the shellac was slightly better than the oil varnish. AP and HE-wise, there was serious flaking of both, but neither were any worse than the bitumen plastic coating. Attacked by chemicals, and I don't mean chemical weapons, I mean solvents, petrol, diesel oil, lubricating oil, and other materials, both were generally okay. The shellac one, however, was more okay. The material made from oil varnish would actually soften and become weaker in the presence of oils and petrols. So the shellac one was a little simpler to apply and a little less likely to have to be reapplied due to some careless refueling or refilling of the vehicle. The work, therefore, was really very promising. It both protected against magnetic mines, and both had some camouflaging properties by virtue of the texturing. And field trials were arranged with the 1st Canadian Army in Zip in Belgium on the grounds of Castle Van Bever.
To this end, 2 tanks, a Sherman and a Stuart, were coated with bituminous plastic, and 2 more, a Churchill and a Cromwell, had a combination of the plastic material and S mines fitted. Visitors attending the trials were invited to examine the coating and to try and get a German deactivated magnetic mine to stick.
Those Canadian field trials showed that the material was acceptable for use, but once more improvements were demanded, specifically to reduce the burden of application time, something the Germans didn't like either with their material. What was wanted by the Allies was a mixture which was easier to apply post-production, quick drying, allowed for the addition of texturing materials such as straw, a material which was resilient and did not flake off. Now, one of the other conclusions of the trials was that the German S-mine was very effective. It basically has a kill radius of 15 by 30 meters, but was also declared to be not much more advantageous than an ordinary number 36 grenade. The S-mines also were found to cause a lot of damage to the tank which was firing them. So the S-mines were not going to be ideal as a means to keep the Germans from getting too close to the tanks, such as sticking on magnetic mines. It is wholly unclear why then, a short while later, that the successful coating material was decided not to go forward with trials, but that further trials of using S-mine dispensers was agreed to be carried out. So quite why that's happened is a little unclear, but clearly someone had a bee in their bonnet and they really kind of like these S-mine discharges. What it also said was the camouflaging effect by mixing straw in with the plastic was effective. Once painted over, the camouflaging effect was most excellent. Despite the potential, however, questions had been raised, And here we have our clue as to why they didn't want to go forward. The head of the Royal Armoured Corps was questioning the value, comparing them to the cost of the actual material. As in, if we spend X on a material, we invest Y number of man hours, what's it really going to produce in the end in terms of protection? So with that out of the way, we're now having to consider another possible solution. And that comes in the form of cementitious rubber. Now, this is a separate project, all within the auspices of an anti-magnetic coating. And this project began in November 1944, led by Messrs. Armstrong Cork Limited. And several different compoundings were considered from them and another contractor called Messrs. Semtex Limited. And here we have several different materials. So Semtex Limited produced two compounds. They produced RE135, which was made of reclaimed pigmented rubber. That was a two-part, very robust, rapid drying, easy to apply material. And Semtex also produced Semtex 484. This was a new composition and would be one single coat, take 1 to 2 days to dry, and would stick to paint. Armstrong Cork Limited produced 5 different options. They produced PR120A, a type of reclaimed rubber, which they demonstrated on unpainted steel, PR120A on primer painted steel. Then they presented YT76, which was made with latex on unprimed unpainted steel, YT/F, which was latex cork on unpainted steel, and YT/F, another latex cork material on on unprimed painted steel. So in a nutshell, we have quite a few different options going on there. And the initial analysis didn't take very long. In April 1945, RE135 from Semtex was found to be simply too soft, and the concerns was that it would simply catch fire when attacked with a flamethrower. Semtex 484 was promising, but Armstrong Cork PR120A was satisfactory. That's the one they wanted. But just to be clear on it, and to make sure that they were doing a fair test, a single vehicle was painted in 2 halves with 1 compound on each side by March-April 1945. Now, this is obviously coming into the final stages of the war, and is actually after the first official British Zimmerit was named. So this isn't some pie-in-the-sky project. By the time of that Semtex and Armstrong Cork work coming into fruition in March-April 1940, there is a British Zimmerit. That is, in January 1945, anti-magnetic compound number 1, also known as AMC number 1 or AMCO, or even AMCO number 1, was officially approved. And this was the bitumen material originally applied to the Churchill. It does not say in the record if the bitumen material is applied with fabrics. I believe not, simply because they didn't mention any of the fabrics within it, which is something you would want to specify given the fabrics that they had tested at this point. So this appears to be a relatively simple bituminous compound sprayed onto tanks. And yes, they're going to be black and they're going to be painted afterwards, but AMCO number 1 was officially approved in January 1945. But AMCO number 1 was not the first British Zimmerit. No, because AMCO number 2 was actually the first British Zimmerit. AMCO number 2 is that shellac material. Think back a few minutes ago, the shellac material, even though it was slightly more easily damaged than the oil varnish, it was much more easily applied because it was easy to spray on and was formally approved. And with the approval of AMCO number 2, they retrospectively approved AMCO number 1 as that bitumen. So technically speaking, AMCO 2 precedes AMCO number 1 in the officialdom of naming, even though it postdates it in development. 30 tons of AMCO2 were going to be demanded by 21st Army Group for use in Italy, but due to shortages, only 20 tons was going to be made. Half of it was going to be sent to France, and the other half was going to be sent to India, that is for service in the Far East, in a colour yet to be chosen, which once more tells us that we are going to be looking at a green coloured material for AMCO2. The shellac-based paint is green, and we know it's green because we also have the composition of it. And this is officially listed as olive drab dark, AMCO number 2, February 1945 ingredients list. And it's quite a complicated list with a lot of numbers, but we have seed lac, which is the shellac base, methylated spirits, pine oil, lithopone, ochre, wood flour, vegetable black, and pigment green B. So those are the material ingredients that go into olive drab dark AMCO number 2. Now, substantial quantities were being wanted for Southeast Asia Command, that's SEAC, S-E-A-C. In fact, so much so that they wanted enough to coat 3,700 vehicles. Production of that much material would require large quantities of shellac, in excess of what was already available. It would also involve multiple manufacturers. In the short term, however, 100 tons of this olive drab dark AMCO number 2, or AMCO number 2 suitably coloured to whatever they wanted, one assumes assuming it's not a pigment that's in very short supply, 100 tons could at least go out in the short term with the appropriate solvents. In order to meet that requirement, for the first 100 tons, raw materials were going to be needed, and these were ordered on the 15th of March 1945. And this is Baizaki seed lac, 7 tons of that, methylated spirits, 61 OP methylated spirits in fact, 16 tons of that, a ton of pine oil, 45 tons of lithopone, 23 tons of natural South African ochre, which for reference is 58% iron oxide, 4.5 tons of wood flour, 4.5 tons of vegetable black, half a ton of pigment green B, and then some additional thinners as well, 2.5 tons each of methylated spirits, 61 OP, and butyl alcohol. In order to help meet SEAC's demand, production of this material was also going to be allowed in India at various paint firms there. They had a well-developed paint industry, so there's no reason that they couldn't also supply some of their own needs. They, however, would have to get an amended AMCO number 2. Now, this isn't AMCO 2 India or AMCO 2 Star, it just simply says amended AMCO number 2. And that is seed lac, pine oil, lithopone, ochre, wood flour, vegetable black, pigment B, and methylated spirits. 64 OP methylated spirits, so slightly different. And the seed lac here is either going to be that Baizaki or the Kashmir type. So it's going to be a slightly different composition because that's the nearest material available suitable. So that would be a little different. And in fact, by April 1945, shortages of key materials like these shellacs had diverted production efforts into yet more experimentation to try and find alternatives. Trials in April 1945 of AMCO 2 coated Shermans and Churchills were done with additional wood wool added in to improve the softness of the visual texture. And this once more showed it was extremely effective as a camouflage. AMCO 2, therefore, as a recipe, was amended once more to improve this texturing and colorization. And the ingredients list is very much the same sort of thing, but in different quantities. We've got 23.5% seed lac, 0.9% pine oil, 42.7% lithopone, 21.3% ochre, 4.3% wood flour, 4.3% vegetable black, 0.5% fast pigment green bee pulp. That's a slightly different thing. It's previously described as just pigment green bee, and 2.6% methylated spirits, 64 OP. And then again, substituting the shellac, by the end of April, we come up with a formal AMCO number 2 shellac substitution. 27th of April 1945. It's now using orange shellac, dark rosin, methylated spirits, pine oil, and either castor oil or cotton stearate, depending on what is available, on top of the other materials, the lithopone, ochre, vegetable black, pigment green bee pulp, wood flour, and 61 OP methylated spirits. I know this sounds really exciting to people who love chemistry. All the recipes are clearly laid out in my book on the subject. But the important thing to remember here is this is a production question. We've identified a need, we've identified a material, we've applied the material, we've tested the material, and the material works. We have shortages of the material, find substitutions to make this work. This is what this is about. And it's this hard work that makes the material better. They're not rolling this material out as fast as they can without really thinking about the effects on industry. In fact, they're working very hard to use stuff that's already on hand. This is quite a well thought out process. The bigger issue, however, going through all of it, was the labor intensive nature of application. A Churchill tank alone took 55 man hours over 2.5 days. It also used 304 kilograms of additional material. 304 kilos on your tank is not a small additional load. A Cromwell, being a smaller tank, 267 kilogram burden on materials. Comes out in May 1945, so right at the end of the war in Europe. And we have new formulations for AMCO number 2 ordered to go into trials that month. And here we have 4 formulations. Formulation A. This is AMCO number 2, but plasticized with castor oil. We have formulation B, plasticized with manila solution. Then we have formulation 333-51-1, and we have formulation 55/2. Those last two are from Jensen and Nicholson, and the exact makeup of them is not entirely clear. It's a little unclear as to who asked them to submit it or quite why. But nonetheless, these were 2 additional samples, and they could well be the same formulations as some of the other ones, but from a different manufacturer, because formulation A was from the Keystone Paint and Varnish Company, and formulation B was from the Walper Moore Company. So this could well be a case of trying to get different manufacturers to supply it. One thing that I haven't mentioned is the exciting world of grinding pigments into the correct grain size, which, if you know how paint is made, is actually a very technically complicated process. So here I suspect that the developers are wanting to see which one is better from different manufacturers, even using the same variations. And in fact, dozens of different compositions were under trial by July 1945. But of them all, they fall into 3 main formulas. So the main formulations of AMCO number 2 by July 1945 are the original formula, the variation formula, which had proved very well from Messrs. Mander Brothers, and the mass production formula, which one could assume is the one you're making the most compromises on material. And the difference between them is relatively minor. So the original formula, for example, was 6.9% Baizaki seed lac. The Mander Brothers formula was 6.73%. The mass production formula is 7.04%. That does not sound like much difference, but when you're making hundreds or even thousands of tons of material, That is a huge difference. More importantly, though, is the switch from 61 OP methylated spirits to the mass production formula using nearly 19% 64 OP methylated spirits. Again, as production was to ramp up, mass production would increase the quantity of pine oil in the substance and reduce the quantity of lithopone, because pine oil was more readily available than lithopone. South African ochre, which in the original formula was just under 9.5%, would in the mass production formula be over 21%. Vegetable black in the original formula, less than 0.5%. In the mass production formula, just over 4.25%. The same for wood flour. The same for pigment B. There was no pigment B in the original formula. The Manda Brothers formula added 0.45% pigment green B. Mass production formula, we're going to get rid of pigment green B and substitute the cheaper and more readily available pigment green B pulp at a slightly higher percentage. The one entity which remains virtually constant the entire time is the wood flour, which is the real texture of the material and also the bit that bulks it out the most. Across the original formula to Messrs. Manda Brothers to the mass production formula, the quantity goes down only from 4.72 to 4.48 to 4.27%, which is a very small reduction in the quantity, and that's because it's such a key ingredient and wood flour is relatively easy to get. By 1946, in fact, work was continuing with a paint, but now looking at another option, and that's a nitrocellulose base as an alternative to all of those other options on AMCO number 2. As if they didn't have enough going on, they're now looking for an even better option. And in 1946, in the month later in 1946, so February that year, the developers in Britain for the first time got original unapplied Zimmerit in barrels The next step was that in March 1946, it was also being considered that this new material coming online was maybe even more interesting than it was first thought. And in fact, it was suggested to build the material into something called a Wesch absorber. And this was copying German ideas for a similar material which had been used to coat the schnorkels of German submarines to make them resistant, make them invisible to radar. Now, the Wesch absorber used a square pattern, approximately 20 millimeters in diameter, with a smaller square in the center, about 6 millimeters in diameter, of a ridged pattern, and in cross-section all of the ridges are triangular. And the purpose of this is that the radar waves come in, they bounce, and they're absorbed, so they're not reflected, so the vehicle is effectively invisible to radar. Battlefield radar in 1946 is quite an advanced thing, put it that way. So to be already thinking about how to build in radar invisibility, for lack of a better term, or certainly radar hiding from radar in 1946 is quite advanced thinking, I think. That would actually go further, and by 1947 there were actually infrared reflecting variations on offer too. For reference, that's the L3H5 series of British Zimmerit, was to be reflecting infrared, and that is to try and hide your vehicles once more. If we're going to go to the effort of putting this fabulous material over our vehicles, it should at least be resistant to enemy fire, make us invisible to radar, make us harder to see on infrared, and make sure that magnetic lines don't stick. So if we take just half a step back again to the recovery of original German Zimmerit, this was identified formally as AMCO number 3. And there was a fourth variation, AMCO number 4, also identified. Unfortunately, no one seems to have quite properly recorded exactly how it differed to AMCO number 3. However, a Cromwell tank T1875572 was coated with both AMCO 3 and AMCO 4, and the effect is striking. In appearance, the tank appears to be almost soft and covered with mud, really, for lack of a better term. What's most important is that you can clearly see ideas of the corrugations in the armor in the coating are gone, and also, just as we mentioned before, that wesh absorber concept had not started yet either. But importantly, they've literally just realized that all that matters is the thickness and not necessarily the front texture. It still has that camouflaging ability. Now, AMCO number 3 is surprisingly similar to the German material, and we know what that is. So just to remind you, the German material was 40% barium sulfate. British Zimmerit, so AMCO number 3, is 34% barium sulfate, although the ingredient is actually mentioned to be a thing called spar or barite. It's the same thing. The German Zimmerit was 25% polyvinyl acetate. The British Zimmerit substitutes lacquer, so 36% lacquer substituting for that PVA. And the lacquer was 85% molith in alcohol and a 15% resin in alcohol mixed together. The German substance was 15% various types of iron oxide pigment. The British Zimmerit is 17% zinc sulfide and ochre mixed together. So the German is 10% zinc sulfide. Let's add that together. So 25% of the German substance is ochre and zinc sulfide mixed together. The British have reduced that to just 17%. The Germans added cellulose fibers, that wood fiber, 10% of that. The British, however, reduced that to 5% using a very fine sawdust. And if you've been keeping up and you're like quick maths, you'll notice that that doesn't add up to 100% for the British Zimmerit, because the British also add an extra ingredient, 4% kieselguhr. And kieselguhr is a type of soft white silica sedimentary rock. It has a low density, it's easily pulverized into a fine powder, and it's widely used in industry and agriculture. It's also, for reference, used in fireproof safes and ovens. And really, this is another bulking agent and another cheap agent. So AMCO number 3 is the British form of Zimmerit, even though we already have, by this time, knowledge that AMCO number 2 is really a bit better. So AMCO number 1, bitumen; AMCO number 2, shellac; AMCO number 3, British recipe improved Zimmerit; and AMCO number 4, something slightly tweaking that AMCO 3 recipe. So, what have we got? Well, there was actually a bit more to the story than this, but not all of it is available. Some of it is lost, and some of it is in American archives as well, because there is an American material as well. But just in summary, in terms of materials, to create the gap between the tank hull and a magnetically attached mine, there were different materials tested. We're not talking about the wire and the wood. Different actual paints / coatings tried. The bitumen emulsion, known as Indasco, that worked. The rubber latex emulsion, that works. A water-based emulsion using polyvinyl acetate, again. An oil-bound paint. The shellac plastic, AMCO number 2. Zimmerit itself. The American compound, which is the SAF/T/DEK, the safety deck. I really hate that kind of thing, but safety deck, an American compound, also worked. and that actually is a non-slip flooring in other worlds. A rubber latex cement, an asbestos cement, and a urea formaldehyde plastic. So those were the main substances. And all of those got tested at one point or another. The bitumen plastic, as we put down, as we mentioned before, is easy to apply. It's quite thick. It is, however, relatively easily damaged by contact with solvents like petrol, and it has a long drying time and is difficult to make stick. AMCO number 1, therefore, is abandoned in favour of AMCO number 2, the shellac plastic. The other option, rubber latex, is cheap, plentiful, sticks easily, requires multiple coats, and it burns. So that's a no. Polyvinyl acetate, again, polyvinyl acetate emulsion, sticks well when the mixture remains well mixed. It is unstable, and the elements easily separate. It's difficult to apply, and it's difficult to manufacture because of the shortage of PVA. The oil-bound paint option, this is simple, it's easy to colour, but it's not possible to make it thick enough. So unless you're going to add hundreds of layers, oil-bound paint wasn't an option. The shellac plastic, AMCO number 2, was excellent. That's the excellent results obtained with the first batch. That's the official quote on the report. However, inconsistent results were obtained from later batches, suggesting some quality control issues. Shellac resin was the substitute for polyvinyl acetate, but despite its potential, AMCO number 2 was abandoned, which is a little disappointing when we know from what I've just said it was able to be pre-coloured to suit the need. So really, to me, AMCO 2 is actually superior to the original German Zimmerit itself. Option 6, the reconstitute, just make German Zimmerit to the German recipe. It's already known to work. It has to be painted because it's not self-camouflaging, and it is difficult to apply, and as well as relying on PVA. So that's not ideal. The American safety deck was nice and resilient. It was very good at resisting damage by shrubs and bushes and things like that. It was quick drying as a varnish. It was easy to apply, but it wasn't very thick. It required multiple coats, and even after multiple coats, it could remain soft underneath, so it was relatively easily deformed if it hadn't hardened properly. So the American option wasn't there. The rubber latex one I mentioned, that had excellent weatherproofing protection because the surface was hydrophobic, so water would just come straight off it. However, it had to be applied quickly. It would harden very quickly, so it was difficult to apply. And it would also dissolve in the presence of petrol and oil. So that was abandoned in favour of the shellac plastic. Again, AMCO 2 was superior to all of these so far. Asbestos-based cement could be applied by a spray gun, but it did not stick well to steel. And the final one, the urea formaldehyde plastic. The setting time would be modified with an inhibitor, but it was difficult to apply, and hardness could take between 1 and 7 days, which is no good at all, because the material would either end up too spongy or it would end up too brittle. So that too was abandoned eventually in favour of the shellac plastic. So now you can see why when the German material, we know as Zimmerit, came along at the start of 46, suddenly it's like, great, we're going to copy this, substituting in the materials we can't find. And I laid that all out in a rough timeline of how it all works. So let's summarize very quickly. 4 main types of AMCO. AMCO 1, bituminous plastic. AMCO 2, shellac-based paint. AMCO 3, the amended German Zimmerit. And AMCO 4 is the amended AMCO 3. So I hope that has been enlightening and not too confusing and not too dull. I know that paint is not the most exciting thing to do with tanks. People like guns and armor and all that exciting stuff. But if you don't want to get shot or killed, what colour your tanks are is quite important. And if you want to win the war, you do have to pay some kind of attention to production issues, as well as the fact you don't want to take half your tanks out of combat for a week while you paint them. So those kind of issues are important, and those were interesting to me. And as I say, they are detailed in my Zimmerit book. Oh, I'm sorry, I nearly pointed at my new book, Striding Ashore. This will be out very shortly. So Zimmerit there, that is available from all fine retailers and from Amazon. There will be a link in the video. But by 1947, unfortunately, the work has been abandoned. The British just kind of, it was done. Either they'd learned everything they wanted to learn, or they'd decided it wasn't worth the effort. But there have been, over the decades since World War II, the occasional re-emergence of some soft coatings on vehicles. And indeed, you can see how effective that softened outline is with something like the Barracuda camouflage system, which is probably the most modern way of thinking about this. No one, after all, is worried about magnetic mines anymore. So what we have there is a relatively brief insight. I know this video seems to have gone on a little longer than maybe you thought it would, but a relatively brief insight into the process of identifying an enemy weapon, identifying why it might be useful, deciding you want it, putting it into practice, testing it, manufacturing it, delivering it, and how difficult that is in an era where you have critical shortages of even the most basic materials like PVA. So that for Britain was the biggest hurdle. If it was not for that shortage, it is very likely that AMCO, or one description or another, would have been in use by the British during the war. So that's it for now. I hope that was very interesting. If you do like this channel, any of the content I put out, then please do that, like, subscribe, tell your friends, all that business. Please do share the videos. I would like to build up a bit of a bigger base of people who want to know about this. And if you are a model maker, learning about the different types of AMCO and Zimmerit is hopefully kind of interesting to you, particularly the photographs in this video. I will, as I say, put a link to the book if you want to put it on the shelves. It's relatively inexpensive. I try and make my books as cheap as possible, so cheaper than they would be through a mainstream retailer. And the Zimmerit stuff will lead us nicely on to talk about Striding Ashore when this is out. This is a proof copy. That's what the grey band is. As you can see, it's a good sized book. So we'll be talking about more materials science. Gosh, I know you're all going to be dying to know about War Department pressure plastic and asbestos sealant and all that good stuff we've mentioned in previous wading videos. So that's it for now. Thank you very much for your time. Goodbye.